Alrighty then. So we have a lovely, really large class here today. Everyone here is amazing. Thank you for being here. So, class. Okay, good. Thank you. All right, that's all that matters. So, determining the concavity of a function. So, for this one right here, it is y equals x squared is concave up, where the square root of x is going to be concave down. All this is concave down. And it has to do with my derivatives. So determining concave up or concave down. Let f be a function that is continuous on a closed interval and differentiable on the open interval. No derivatives at the endpoints. That's important. F is concave up on a to b if the graph of f lies above each of its tangent lines through a to b. F is concave down on a to b if the graph of f lies below each of its tangent lines through a to b. Test for concavity. Let f be a function that is continuous on a closed interval. Suppose f prime and f double prime exist on the open interval, a to b. F double prime is greater than 0. That means f double prime is going to be, what numbers are greater than 0? Very good, positive numbers. Okay, if double prime is greater than 0 or positive numbers on the interval here, then it is concave up. So there is a slight conflict with these ones right here. So let's take a look. Now throw up those gang signs. Show me concave up would be like this, right? Okay, what type of parabola do I have there? I have a positive opening parabola, right? But in this right here, what does it give me right there in the middle? A vertex. But what type of vertex is that? What type of point is that? It's a minimum, right? So it's kind of counterintuitive for this. So if it's concave up, I have a minimum, but the second derivative is going to be positive, right? F del prime less than 0, open interval a to b, then is concave down on the interval from a to b. Note when f prime and f del prime both exist on the open interval and the function f is called twice differentiable on a to b. See this right here? This is actually terminology you're going to see all the time. That means that the derivatives exist, and I can take the derivative on all points that do exist. Make sense? No? Maybe. So I could take the derivative twice for that function at all points in between. Show that this is concave up on its domain. So, first thing I'm going to do is I'm going to go from f prime of x is going to be e to the x. Okay, and f double prime of x is e to the x. Now, go back to last slide. So it's got to be greater than 0 for it to be concave up. Okay, so what value is at e to the x? Okay, so e to the x for my domain, because unless you know what e to the x looks like, you're going to struggle right here.
Are you talking about the domain, like the x-axis part of it?
Yeah, e to the x.
Negative infinity to
Infinity. There's no place that it's actually not.
oh yeah. So I thought it had a vertical asymptote.
I'll pull it up. Where would it have the vertical asymptote?
I was thinking that, but no, it does go like forever. Like.
Yeah. All right, so here we go. So I'm going to graph this so you guys can visualize this now. So e to the x. So, is there any place that this is undefined? No. Okay, there we go. Does it equal 0? No, it does not. It does not equal 0. So if I go back to here on my rules, can I say that 0 equals e to the x? No, I cannot because it does not equal 0. So now let's start looking at numbers in between here. So if it doesn't actually equal 0, is it going to be a positive or negative? So let's look because I'm looking for my second derivative here. Okay, second derivative. So that's going to be right here for either one. It could be this or this because they're all the same. So let's plug in numbers. So let's go. All right, what is e to the first? It's like 2.7, right? Approximately. Here, I'll pull it back up. So e to the first. So when I approximate this and say e to the first is 2.7, I'm just going to assume it 2.7, okay? So my e value, so you know what we're actually working with here. Because if I say pi, you think of what number? 3.14, right? We're talking about e to the first, should be thinking of 2.7. That's the approximation for that all the time. So if it's -1, wouldn't it be e to the -1, which is the same as saying 1 over e to the first, which is 1 divided by 2.7, which is less than half. Is that positive? Yeah. It is positive. That's what I'm going for here. So this right here is positive. That's important because my second derivative, if it's positive, what do we know about the concavity? Yes, very good. It's concave up. Now, I'm going to pick another number. If you notice, it really doesn't matter because if I'm looking at my graph, it's not changing anywhere. It's all going this way, right? Okay, so I'm going to pick a number. Let's go 3. Sorry, there we go. So if I pick a number, positive 3. So again, we're going to approximate this. So mentally, I want you to think about this. What is e to the first power? It's 2.7, right? So it's basically so to the third power is basically saying 2.7 to the third. Yeah? Or you get like A1? No, it's not.
Calculator says 20.08.
20.08?
Yeah.
Okay. So 20.08. Thank you, Blake. Now, what do I know about that number? It is positive. So, by testing these two numbers, what can I say about the concavity? Concavity, it is concave up, because I'm proving that it is a positive number over the interval. There is nowhere that it is equal to 0. So my first derivative is not equal to 0 anywhere. My second derivative is not equal to 0 anywhere. My function is not equal to 0. So if the function is not equal to 0, that means it does not cross the x-axis, right? So everything is in the positive y values. So that's how we're proving right here. It doesn't equal 0, so that means it's either all going to be positive or it would be all negative. So if it never crossed the x-axis, we get both of those. So this right here, it is concave up on its domain. What is its domain? Yep. All right, finding local extrema, determining concavity. So I'm going to go another page on this one. X cubed 6x squared plus 9x plus 30. It's minus 6x squared? Thank you. Ah! Okay. All right. So we're going to go down the list of things to do. My function, if I set this to 0, what do I get? If I set it equals 0, what do we get? Zeros, which are technically where what? What happens? No. The function, remember? Crossing the x-axis, right? Okay, everything has a reason. So if I set this equal to 0, that would give me where it crossed the x-axis. I don't need that right now. But if I were to be graphing this with my derivatives, those are the things that I would do. F prime. 3x squared minus 12x plus 9. What does this give me? When I set it equals 0, it gives me mins and maxes, right? Set it equals 0, I'm going to have a min or max. So I'm going to go right here. 0 equals 3 quantity x squared minus 4x plus 3. 3 quantity x -1, -3. Right here, I get x equals +1, x equals +3, and these are those are going to help me with min maxes.
We need to find out which ones are which.
We will in a second.
But when it says local extrema, I mean you found the local extrema. So do you technically need to specify what is the min and max?
Heartbeat. I'm just doing all the work right now. All right, so we got that. Now, I'm going to change color for my second derivative so we can see. All right, second derivative. So f double prime of x is equal to 6x minus 12. Set it equal to 0. 6 quantity x minus 2. And I get x equals 2. Now, what does this give me for my second derivative? Did I spell it right? Or is it with an E? Inflection?
That's right.
Yes? Good. Okay. So, my second derivative equal to 0 gives me my points of inflection. Points of inflection is where it changes concavity. That's when it's going to change from concave up or concave down. So if there's only one point, what does that tell me? It's only going to change one time, right? There we go. It's only going to change one time. So that means that half of it's going to be probably concave up, the other half concave down, or vice versa, like all.
Does the number of times that it changes from concave up to concave down have to do with degree?
Yes, all of it has to do with degree. Think of x squared. Show me x squared. Okay, show me x cubed. So you're basically like this, right?
Yeah.
So x cubed is like that. And x4?
Has like the end thing.
One, like that. That would be an x4, right? But both ends end up going back up, right?
Yeah.
So yes, because if I do that, I have two going up, and where my fingers come together in the middle would be one going down, wouldn't it? So I would have a concave up here, and where they come together in the middle would be a concave down. So yes, it does. So, but yeah.
So is that one less than degree?
It should be. That's going to be how many mins and maxes we should have. Or could have. That's a better way to say it. Could have.
You have one less. Oh, because I suppose if it doesn't like.
Yeah, if it doesn't change. So if it's x to the fourth, it's going to look like a parabola. It just goes up faster. But there is, because of that, I could have 4 possible zeros if it was a function, right?
Yeah.
So there we go. All right, so points of inflection. So let's see. So I'm going to take the information from my first derivative. Information from my first derivative. I have a min and max, but I don't know which is which yet. So I'm going to plug these into my second derivative. So f double prime of 1 f double prime of 1, it's going to be 6 minus 12 is? Negative 6. Now, what does that tell me? Okay, keep this in mind right now. I'm going back over to the notes. If f is greater than 0, f double prime of x is greater than 0. No, that's not. If f double prime of x is less than 0, then it's going to be concave down. So, at that point, it's concave down. Now, with your hand, show me concave down. Throw up that gang sign. Concave down. Concave down. What does that give me? Does that give me a min or a max? There we go. Concave down is going to give me a max.
Wait, how do you know? Sorry, just like, how does it work when you graph the second derivative? How does that give you the
Okay. Here's my hands, right? Derivative equals second derivative equals 0. That's where my fingers come together in the middle.
Yeah.
Okay? This over here is all concave up. This over here is all concave down, right? So I check my points, which is my points where my slope is equal to 0. That's my min and max, right?
So is the second derivative the graph of when it's concave up, when it's concave down?
So if I graph the second derivative, everything that's positive,
Concave up.
everything that's negative, which is below the x-axis, is going to be
Concave down.
yes. Yeah. So again, throwing up those gang signs, hopefully this helps you out. That right here it's negative, so this is concave down. F double prime of 3 I get 6, right? 6. It's positive, so therefore it's concave up. So if it's concave up, that tells me that is a, if it's concave up, that is a min. And if it's concave down, that tells me that is a max.
Which way do you find easier, the number line method or this one? Because there's the one where like, you find where it's positive and it's negative.
Okay, so that has to do with only the first derivative test. This is using the second derivative test.
Oh.
There's times in which I cannot use a second derivative test. When do you think that would be?
When your derivative or second derivative is or when your first derivative is a whole number and you derive it.
So it's not derivative again, right? So it's not twice differentiable. That was key, and that was the vocabulary that they were trying to say. So twice differentiable means that you could take the first derivative, it's all continuous through there, and you could take the second derivative, it's all continuous through there. So if we can't take the second derivative, then you are stuck with first derivative tests, draw your number line, positive negatives. Okay, what if it comes up to a cusp or a corner? Then you can't take a derivative there, but you still use the first derivative test.
Do you think the first derivative is better for everything?
Depends on when it's asking for it, alright? So this says prove it and show this. Yes, Blake, what's up?
Are these ones you said right here, how they're the min and maxes? Are they like the percentages? Like how do you know that? Like I know how you know that the concave down up, but like
Okay, I'm gonna go and graph it now. Let's graph the function, okay?
yeah, like could it be any other point on like maybe
Okay, yes. Good point. It could be, if you notice right here, x equals 2. So my second derivative, I could pick any number to the left. That's going to tell me the concavity for everything to the left. I could pick any number to the right. That's going to give me any number going to the right. That's all concavity because the concavity doesn't change again.
yeah.
So yes, you could have used 1 and 3 and said because of, oh, not 1, yeah, just numbers to the left and right. So it over those sides, you could have just picked numbers off a number line and actually checked it.
Yeah. But then like how do we know that those are the min and maxes specifically?
Okay, first derivative. First derivative says my derivative is equal to 0 at these points.
Yeah.
So what's going to happen? So right here, derivative equals 0. That means it's actually the slope is going to be 0. So the slope going up to right here is going to be 0, and that's where it changes to go back down.
Oh wait, so those are the only points where the slope is gonna be equal to 0.
Yep. That's the only points right there where slope is equal to 0. So that's why I know they have to be mins and maxes. Those are my local mins and maxes. Okay.
We didn't answer that last part.
Yeah, there it is right there.
Did we just say that?
Huh?
Did we just say that?
Yeah, so right here, this is what it's asking for.
So just concave up at that point.
And concave up, and where's it concave down?
Really? Which is that?
So from
It's
this.
asking like from where to where, you know? Like like X equals.
Oh, okay. I know what you're saying. Yes. You're right. Okay, so now everything to the left of 2 is negative, right?
Yeah.
So from negative infinity to 2 is going to be concave negative, so it is down. And from 2 is concave up. Yes. I'm sorry. I wasn't understanding what was being said, being asked. So, but yes, you're right. All right. There we go. All right. Let's go. Definition, inflection points. This is what we talked about for the second derivative. Suppose a function is differentiable on an open interval from a to b containing c if the concavity of f changes at point c, comma f of c, then c, comma f of c is an inflection point. So, for it to be an inflection point, what has to happen?
It has to change.
Very good. It has to go from positive to negative. So it has to change. It doesn't have to go positive, negative. It could go negative, positive. But it's got to change signs. It has to change signs. Okay. Function differentiable open interval a to b containing c, f of c is an inflection point of f if f double prime of c is equal to 0 or f double prime of c does not exist. Now, that's key. If the second derivative does not exist or equal to 0. So on that previous problem where I did that, I got x equals 2, right? Or any undefined or any non-real. So any undefined or non-real would also get me my does not exist.
So, like, is it saying, like, if the so if the first derivative is an inflection point, then is that what it's saying?
Then you,
Then
yeah, the first derivative, right? The first derivative. So
yeah.
yes.
And then it's so basically the second derivative won't, at least at that point, it won't exist.
You would get does not exist. Yes.
How would it not exist? Would it not exist when it was like, if it was like piecewise or something, where it wouldn't?
That would be one example. Off the top of my head, I can't spit out anything.
Could it not exist and still be?
When you take the derivative, what do you do with your exponent?
You like subtract one. And then
Subtract one, right?
and
And if you end up subtracting one and we end up getting to the point where we have 1 over x, right?
then it's 0.
Right here. And if it looks like this, then you can't have.
So is it more
Yes, right there. So that is, why is there a domain restriction? Because it is undefined. It would be a domain restriction if it is non-real. Inside a square root, I cannot have what types of numbers? Can't have negative. So if I end up with something like this, x has to be greater than or equal to 0, right?
Wait, are there non-real points of inflection?
Yeah, but we're not dealing with those. Because when do we deal with those?
I don't know.
Yeah, those are like polar type of. Go ahead, Lee.
So, math, if you were suppose you were to find the first derivative and you didn't graph it yet, so you wouldn't know if it's a point of reflection yet, right? So.
Okay, yeah, so hold on, I think the next one actually has, here's all the tests. There's another problem. Here it is right here.
So, are you supposed to like find the second derivative and then plug it in?
Yes. You ready? So step by step. So the question you were just asking, right here. Let's go through and actually talk about this. Doing the problem right here. So f of x equals x to the 5/3.
Yeah. So to find the inflection point, find the second derivative.
Yes. So let's go first derivative.
First derivative.
What's the first derivative?
5/3 to the 5/3 x to the power of yes, 2/3.
Minus 3/3, right?
Yeah.
You're subtracting 1, so that's going to give me
2/3.
2/3. Very good.
And then,
Okay, so that's the first, right?
yeah. So the second
And then second derivative.
would be 10/9.
So it's 10/9. X to the, yep, -1/3. So let's go ahead and rewrite this.
Oh, you can do
10 over
9x
to the,
1/3.
all right? So in this case right here, x cannot be what?
X
It can't be 0, right? Because why? I can't have 0 in the denominator, right?
Oh yeah.
Okay, so now to that 1/3. 1/3 means that it is the third root of x to the first. That's what the 1/3 means, right? Okay, am I allowed to have negatives here?
Yes, because it's a cube root.
It's odd. So I'm allowed to have negatives. So I can take the third root of -8, which is going to be -2 times -2 times -2, right? Do I have 3 of them? Did I just blow your mind right there?
No, I did that, but how do you? But they said that the definition was if it's already an inflection point at the first derivative, right?
So right now, no. First derivative gives me
Gives me the mins and maxes.
mins and maxes, right? First derivative gives me mins and maxes. So let's take my first derivative. Set that equals 0. Yeah, it's going to be 0. It's going to be 0, right?
Yeah.
Okay, so I get x equals. So that means that is going to be, if it's the first derivative, that's going to be It's going to be a min or a max, right?
Yes.
Okay. And my second derivative equals 0. So 0 equals 10 over 9x to the 1/3.
How would it even?
Go back to the second part of the rule. Equal to 0 or does not exist.
Does it exist?
There we go. Does not exist. So at 0, it does not exist. So that means that is a point of inflection. That's going to be a point of inflection. And it's also going to be a min or a max. So what do you think this is going to look like?
Would it be like the cubes?
Uh-huh. What was the function? It was just x to the 5/3, right?
Yeah.
Okay. So x raised to 5/3. There you go. It looks like the x cubed problem.
So for something like that, it's still considered a critical number, but it's not a min or a max.
It's not a min or max because it's going to that point, but it's not. Remember, what has to happen for it to be a min or max?
It has to go down.
It has to change direction, right?
Yeah, it's not doing the direction.
It's not doing that.
But
So
it's
it's all
still a
positive
critical number?
over the whole thing except for right there where it's equal to 0.
Okay.
So it's not going to be a min or max because it doesn't change direction. Right there, that is my point of inflection. How I test my point of inflection? This is where you were saying, Blade, do I have to pick those numbers? No, I don't. So what I can do, if I know it is 0 for both of them, pick a number to the left. Pick a number. So I'm going to go second derivative. So f double prime of -1 What's the cube root of -1? -1. It's -1. -1 times 9. So I have 10 divided by -9. Is it a positive or a negative? It's a negative. So it's actually -10/9. So therefore, if it's a negative, that tells me the concavity is concave down. This number was neither a min or a max, so I can't say it was a min or max. I'm just checking concavity here. Now, pick something to the right of that. +1. +10/9. It's concave up.
So if there's only one critical point, does that mean it's like it's not a min or a max?
Yeah. There's one. We only had one min-max, right?
Yeah.
Okay, that's my first derivative. And I only have one second derivative, and they're both the same thing. So if it's both the same thing, for it to be a max, it's got to change direction. It's got to go sloping up and going to down. If it's a minimum, it goes down and changes to up.
Wait, the same thing.
My first derivative
I thought that one was 0.
equals 0,
Yeah.
and my second derivative, critical point,
Can't equal 0.
yeah, so they're both 0 on both of them. This one, the first derivative, x equals 0. The second derivative, x cannot equal 0. That's why I check the numbers to the left and right of that.
But if one can't equal 0, doesn't that mean they're not the same?
Say it one more time.
If one cannot equal 0, then doesn't that mean they're not the same?
This is second derivative.
Yeah.
According to the rule of the second derivative, all numbers in the domain at which the second derivative is equal to 0 or does not exist. So we hit that second criteria there, does not exist.
Yeah.
Because that's going to be my undefined point. So that makes it a number for this to test. More practice? Okay, so this right here, I'm going to leave off, and then I'll let you guys mess with this. And then I will change the due date for the assignment since it's supposed to be due tomorrow, right?
Yeah.
So I'll move it to Friday. We'll finish it Friday then. Or we'll finish it Thursday. If I have to move the test back, I'll move the test back also.